physicists, welcome to my video on momentum in collisions. Specifically today, we're looking at momentum in two-dimensional collisions. So we've met conservation of momentum before, but we've been doing one-dimensional problems. Now we're going to think about momentum in two dimensions. If you want more help with this topic, don't forget to check out my resources on the My EdSpace website. And if you want to improve your A-level physics grades, you could even have a look at the link in the description of this video about joining in with the My EdSpace live lessons. So let's get ourselves started. Now, we know that momentum is equal to mass multiplied by velocity, where this velocity here, remember, is a vector, which means that it's got size and direction. So this is going to become really important, okay? Because we've met conservation of momentum before. We know that the momentum before a collision has to equal the momentum after a collision. But what you might not know yet is that this has to be conserved both horizontally in the x direction and vertically in the y direction. Most of the problems that you've looked at before, you'll just be solving momentum in one plane or the other. Now we're going to have a look at solving momentum problems in both planes. So over here, I've got quite a basic problem. So I've got one ball, the green one, hitting into the red ball, and they go off in opposite directions. Okay, these might be snooker balls, these might be hockey pucks on ice, who knows? But what we're going to look at is we're just going to look at this as a bit of an example. So I've got my two vectors of velocity. And the first thing I'm going to do is I'm going to split them down into the vertical and the horizontal components. Or I should probably give you some angles, okay? So we'll call this one theta, and we'll call this one alpha. There we go. Right. So I'm just going to work out the horizontal and the verticals first, because I think that's going to help me. So I'm going to write SOHCAHTOA at the top so that I know what I'm doing. Now, I'm going to start with this side first, so it's the opposite. So I'm going to use sine. So this side here would be V1 sine theta. So then here would be V1 cos theta. This side here would be V2, it's the opposite again, so it would be sine alpha. That side there would be V2 cos of alpha. Okay, so I've just broken down my velocity vectors into the horizontal and into the vertical components. Now I can apply conservation of momentum. So let's start in the x direction, that direction there, because that's the one that we're most familiar with. So the momentum before the collision will be the mass of the green ball, m1, multiplied by the velocity of the green ball, u1. m2 was stationary, so it's not going to have momentum. So this will be the total momentum before the collision. Now I know that the momentum before the collision has to equal the momentum after the collision. And I'm just going to look in the x direction to start with. So the momentum after would be this green ball, so m1 v1 cos theta, added to the momentum of the red ball, which would be m2 v2 cos of alpha. And because momentum before has to equal momentum afterwards, I can write all this out as one big expression. So I've got m1 u1 would be equal to m1 v1 cos theta plus m2 v2 cos alpha. So all it's saying is that the momentum in that direction before has to equal these bits of the momentum afterwards, okay? Right, so I've got an expression about momentum in the x direction. Now I want to think about the vertical momentum, the momentum in the y direction. So you'll notice that actually before the collision, the object m1 was just moving to the right. It wasn't moving up, it wasn't moving down. So it wasn't moving in that vertical plane. So actually the momentum in the y direction before the collision is 0. So I know that the momentum in the y direction after the collision is also going to have to be 0. And that actually figures, doesn't it? Because if you look at my components of velocity here, one's going up, one's going down. So actually, they're going to be going in opposite directions. So I can give one of them a negative sign. I normally say that upwards is positive, downwards is negative. So I'm going to give this one a positive sign, and I'm going to give this one here a negative sign. Right, let's start adding these momentums together. So remember, the momentum is mass multiplied by velocity. So the momentum afterwards is going to be m1 v1 sine theta minus m2 v2 sine of alpha. What I can do now is that actually I know that this whole expression has to equal the momentum before, so it's going to be 0. So I can rewrite this as 0 equals m1 v1 sine theta minus m2 v2 sine of alpha, and rearrange, so I get m1 v1 sine theta equals m2 v2 sine of alpha. Now, at the moment, this is just a whole bunch of algebra. So let's actually look at some real life problems. Let's start putting some numbers in and see how this works in action. Okay, here we go. So behind me, I've got a problem quite characteristic of what we might see in an exam. So I've got a mass, m, which collides with a bigger mass, y, 3m, and then x and y go off in opposite directions. I know this angle here is 60, and I know that this forms a right angle, okay? So the first thing I'm immediately going to do is I'm going to put in that my angle here is going to be 30 degrees. And then I need to find what the ratio of V1 to V2 is. Now, I could do momentum in the horizontal plane, but actually, why would I bother? Because I know that the upward momentum here is going to have to equal the downward momentum there. So actually, I'm just going to do momentum in the vertical plane. So first thing I need to do is work out the components of the velocity. So Katoa, this is the opposite. So this is going to be V1 sine of 60. This one is going to be the opposite as well. So that's going to be V2 sine of 30. Opposite, yes, lovely. So I know that the mass of x, so mv1 sine of 60, is going to have to equal 3m v2 sine of 30, because I know that the upwards momentum has to equal the downwards momentum, because the momentum before the collision was 0 in the vertical plane, so the total vertical momentum after the collision also has to be 0. Happy days. Right, let's see what I can cancel. I can get rid of my m's. That's a good start. Okay, I'm looking for the ratio of V1 to V2. So I'm going to move my V2 over here. So V1 divided by V2 sine of 60 is 3 times sine of 30. Okay, I need to get V1 divided by V2 on its own. So I'm going to do V1 divided by V2 equals 3 sine 30 divided by sine of 60. I'm now going to grab my calculator and pop that in. So 3 times sine of 30 divided by sine of 60 gives me an answer of root 3 or 1.7. So this is how we can find the ratio of the velocities just using these ideas about conservation of momentum in 2 dimensions. Let's have a look at another problem, shall we? Okay, problem number 2 is on the board behind me. We've now got 2 helium atoms. Helium atom A is moving in with a velocity of 500 meters per second into B. They collide and they're going off at angles again. And this time I need to find out what the momentum of B after the collision is. So The first thing I'm going to think about is I'm going to start by breaking down these vectors, okay? So I'm going to think mainly about the vertical plane to start with, because actually that makes my expression quite a lot easier, and it's going to make this problem quite a bit quicker to solve. Because instead of having to calculate momentum before and momentum afterwards, I know the momentum before was 0, so I know the momentum afterwards also has to be 0. So I know that these two momentums have got to equal each other, so it's just cutting down like the stages of working out that I've got to do, which in an exam is quite important because we don't want to be time pressured. So that would be the opposite. So that's going to be 230 sine of 65. This one here, I'm just going to call this vector here V, because I don't know what it is. So it's going to be the opposite. So it would be V sine of 25. Righto. So I know that the mass of the helium atom, I'm just going to put it as M at the moment actually, because I've got a feeling that these are going to cancel somewhere, and if I can get away without using this great big number here, I would quite like to do that. The mass of the atom going upwards multiplied by 230 sine of 65 equals the mass of this atom going down here, mv sine of 25. Actually, I'm working out total momentum, so I will have to use it at some point, but actually I could, yeah, I'm going to cancel. I'm going to work out what V is, and then I'm going to multiply it by the mass. So I've got 230 sine of 65, divide it by sine of 25 would give me this velocity V here. So where do I put my calculator? We've got 230 divided by sine of 65, multiplied by the sine of 65, and divided by the sine of 25 to give me V, which is 493.2 meters per second. Now what I need to do is I need to multiply it by the mass of the helium atom to find the total momentum. So the momentum of B would be 6.64 times 10 to the minus 27 multiplied by 493.2. 6.64 times 10 to the minus 27 times 493.2 gives me an answer of 3.28 times 10 to the minus 24 kilogram meters per second. Now, I hope you found this video useful. I'm hoping you're being a bit more clear about momentum in 2 dimensions. If you want any more worked examples or you want some practice questions, remember to check out my resources on the My EdSpace website. If you want to have a go at improving your A-level physics grades, make sure to check out the link in the description of this video about joining the live lessons. And whilst you're there, you can also follow this channel for more content just like this. I'll see you very soon. Take care now.